Hi everyone. In this demonstration, we introduce Disease Progression Modeling Workbench 360, also known as DPM 360. It is an open source project. It is an easy to install system that helps research and development of disease progression models. In this demo, we will go through the motivation for the DPM 360, give a brief introduction, and we will jump into the demo. Disease progression modeling aims to characterize the progression of a disease and its comorbidities over time using a wide range of analytic models, including disease staging, patient trajectory analysis, prediction, and time to event estimations for key disease related events. DPM has applications throughout the healthcare ecosystem, from providers to payers to pharmaceutical companies. But the complexity of building effective DPM models can be a roadblock for the rapid experimentation as well as adoption. Some of this is addressed by the standardization of data model and tooling for data analysis and cohort selection provided by the OHDSI. However, there are still some unmet needs to facilitate the development of advanced machine learning techniques such as deep learning, which have additional requirements such as experiment tracking for reproducibility. Furthermore, to accelerate the DPM research, a data scientist's available tools should always include a mechanism for rapid prototyping by being able to convert models into microservices and deploying them into a cloud environment. So that is the motivation for our team to build the DPM 360. DPM 360, as shown in this picture, has four key components. It builds on top of the popular OHDSI stack and adds three capabilities. First, it adds a very powerful deep learning framework called Lightsaber. The models trained using the Lightsaber are automatically registered into a model registry, and we have a piece of code called service builder that looks for models that have been registered into the model registry and automatically converts them into microservices and deploys them into a cloud environment. Here we see the overall architecture of the DPM 360. The four key components are an installer that installs the entire DPM 360 stack into a cloud environment such as Kubernetes or OpenShift. Cohort connector is a component that connects to the OMOP database and extracts cohorts as well as their features in a format that is more suitable for deep learning. Lightsaber, as described earlier, is a framework that takes in this data and is able to train a machine learning model. Finally, service builder component takes those models and automatically converts them into microservices and deploys them into a cloud environment. Now, let us go deeper into each of these components as part of the demo. So, here is our plan for the demo. First, we will demonstrate the installer. For this, we will check out the code from the public DPM 360 repository into a machine, and then we will run the installer against a cloud infrastructure. The installer is going to install the entire DPM 360 stack against the cloud infrastructure. As part of the installation, it is also going to load the dsynpuf synthetic data into a database. After that, we are going to connect to a data source that already contains Mimic3 data. Then we are going to show the cohort connector and use the cohort connector to extract features and the cohorts for a particular endpoint. Once the data is extracted, we will show a demonstration of the Lightsaber and use the Lightsaber to train a model against the extracted data. At the end of the training, the model will be registered in the model registry. Once the model is registered in the model registry, the service builder will automatically pick up the model from the registry and turn that into a microservice. We will interact with the microservice that is deployed on the cloud infrastructure to see how it works. So first, we will start with the installation, and the installation demo is being done by Piyush Madan.
For the installation of DPM360, we use Helm charts. We support Kubernetes as well as OpenShift cluster. For installation, we first get the context of the cluster, which may depend on the cloud provider. Then we call a script, which basically calls a couple of Helm charts that take care of installing ODC components, Atlas, Web API, database. It installs model registry part, which is MLflow, database, and object store, MinIO, and service builder. And to persist all the data used by different services like object storage, MinIO, databases, we use persistent volume claims. Now that we have seen a high-level design of how we will install it, let's actually install DPM360 on a cluster in cloud. The repo, you should go to installer folder, and in installer folder you'll find one cluster get context. So that's the very first file that you should modify to basically change the way you get the context of your cluster. It may be different based on your cloud provider, but once you get the config set with the kubectl, we can move forward to installing the Helm charts. Now that we have all the services up and running, I can show you. Here is MLflow, MinIO showed up. Then we have Atlas. Now, what I plan to do now is to load data. To load data, you'll have to modify the ETL YML in your ODC stack folder, where you'll have to provide where your data resides, where the tar.gz file is for vocabs and the patient data. So, and it can be in a cloud object storage where it can pull. You'll have to provide an API key to access that. So modify that YML, give the link, and then you should be good to run cluster to load data. Yeah, you see it's deployed. It will. So the Helm chart is deployed. Now you'll have the ETL started. It will take some time for the entire ETL process to complete. So in this section, we have gone through installing all the different components. We have just started on loading ETL, doing the ETL part, and soon we'll be able to see that data is loaded. Now that we have a working installation of DPM360 with Mimic 3 added as a data source, let's see how we can use Cohort Connector to build cohorts and extract features for training a deep learning model.
We are now going to see how to use the cohort connector to extract features for disease progression modeling in Lightsaber. The goal of the cohort connector is to integrate Lightsaber with Atlas and other cohorting tools available in the OHDSI stack. For example, a user can begin by creating concept sets and defining the target and outcome cohorts of interest in Atlas. The user can then configure the cohort connector with the cohort details and covariate settings desired for training a Lightsaber model. The cohort connector will use these configurations along with custom queries to extract and transform complex time series features into formats required by Lightsaber. For each extraction process, a YAML configuration file is automatically generated. This file specifies the outcomes, covariate types, and file locations of the extracted features. In this example, we'll demonstrate how to use Atlas and the cohort connector to extract features for predicting industrial mortality using the MIMIC3 data. Here, our question is, among adult patients admitted to the ICU for the first time, which patients will pass on within 30 days of this admission? Our target cohort are adult patients who have been hospitalized for the first time for at least 3 days and who have at least one measurement recorded within 2 days of their admission. Our outcome cohort are adult patients who died within 30 days of their first admission. Of note is that we extract the data for the patients in the target cohort, and some of these particular patients are also members of the outcome cohort. In Atlas, we will first create a concept set to define hospital visits. A concept set is just an expression representing different concepts that have a similar meaning. In this example, we have 4 main concepts that define the different types of visits within MIMIC3. Once we have these concept sets defined, we can use them to define our target cohort. Here, a person enters our target cohort when they have a visit occurrence of hospital visits that we previously defined for the first time in the person's history, and with the visit length being at least 3 days and the person being above 18 years. We further specify that only persons with at least one measurement within 2 days of their index admission are included. We can generate our cohort by clicking the generate button that's provided in the Atlas UI. Having defined our target cohort, we can move on to define our outcome cohort. Here, we define our outcome cohort as the cohort consisting of persons who have any death occurrence, where that occurrence is preceded by a hospital visit for the first time in the person's history, where the visit occurred between 30 days and 3 days before the death. Once we have defined this outcome cohort, we can also go ahead and generate it in our MIMIC data. So this notebook demonstrates how we can use the cohort connector to extract data for cohorts defined in Atlas. So the first thing we do is sort of like name our analysis. Once we've done this, we can look at where to store our data as well as where to have as our working directory. And then we can also look at or specify the connection to the DB, which is in the almost ADM format. And this can be done by providing both the username and the password along with the server where the DB resides. Once we do this, we have to know where the cohorts that we had created previously do resides. And this can be specified in this part here. And of note is that you want to be able to know the cohort ID for the target and outcome cohorts, and these are derived from the Atlas UI as we had previously seen. Next, we can look at different settings that we can have when extracting the data. And of interest here is sort of like figuring out, like what are your types of concepts IDs you want to include, whether or not you want to remap them to some given values, which of them are categorical or numeric, and what are their normal values so that you can think about what you use when imputing missing values. The next thing we do is sort of like have what we call modeled training settings. In this example, we are saying that we are going to look at a sample size of about 500 patients, and then we can look at about 25% of this will serve as a validation set, and then we'll use a random seed of about 10 when you're doing the feature extraction process and train test splits. Most importantly, to extract the data, the first thing we do is to define the connection to the cohorts of interest. And we do this by creating an instance of the cohort connector class. And in so doing, we pass a parameter which can either be a path to a JSON file with the connection settings described, or we can essentially declare these settings by passing in arguments that are that have to be uh, used for connecting to the cohort data. In both cases, as you can see, we can get information as to whether or not this connection was successful. Next, we create an instance of the feature extraction class, and this takes as input an object of class cohort connector, along with a path to a JSON file which describes settings for feature extraction. Or we can also again declare these particular settings by directly providing parameters as arguments when getting an instance of the feature extraction class as seen here. Again, in this case, as you can see, we can essentially know whether or not this feature extraction class was successfully created. Of note is that we can extract data for both training and prediction setups using the extract features function. In the training setup, our goal is to extract both the training and validation data that is used to train lightsaber models. This setup extracts and transforms the data into a format that can be used for lightsaber models. As you can see, the extraction process ends with a bunch of files that are created that basically are used to train the data, along with an experiment configuration file that can be used to determine how the experiment will be done. Of note is that this is an example of the output of the data and how it looks like. And we can see that we have it in the sort of like a long format where for each patient we can track the stay ID along with the observations that were made at different time points during the stay ID. So here the columns are basically the features of interest, and the rows here are time steps for a given stay ID for a given patient. And the output here is a single binary outcome that says whether or not the patient died in a given stay. We can get the same info for the evaluation set. And more importantly, we generate a configuration file that describes the different types of data and the parameters that we can use to determine how the experiment will be done. Lastly, we can see that we can extract data for single or multiple subjects, and this can be used to extract data for the prediction phase of any given model training. Now that we have our cohorts generated and data extracted, let us see how lightsaber can be used to train a given model.
Before we see the full usage of Lightsaber and DPM 360 in general to work through an end-to-end example, let us go slightly deeper into the technical capabilities of Lightsaber. As we discussed previously, Lightsaber is designed ground up to provide simple, composable, unified model training framework. It's built on state-of-the-art open source tools, and our philosophy behind this component is to provide a batteries included approach for disease progression modeling. You can see the full high-level technical overview at the link in the slide, but from a high level, there are four key components of Lightsaber. The first component, datasets, provides the user with a standardized method of ingesting data such that they can be used in the most common format for experimentation. It also provides several trainers that helps in training the models using the best practices and with added goodies as we will see in a few minutes. The third component are a set of pre-built common metrics that are used by such trainers for specific tasks so that we can report in a consistent manner for downstream usage. All of this is tied through inbuilt model tracking and support for post-hoc model evaluation using MLflow. The first module, as we were talking about, is related to data ingestion. This is provided by the base dataset class within the data utils function of the Lightsaber library. We typically interact with CSV like raw dataset, and on your screen you see several key components that defines how to use a base dataset. Some of the key concepts in this involves the idea of selecting features through the feat columns argument, which can accept either a list of features or a regex or even a hybrid approach where some of the features could be provided with a list of features, some of them could be provided with partial regex. It also accepts a set of categorical values, which is incredibly useful, especially when we are dealing with large amount of data where the test dataset may not see certain kinds of categories that were present in the training dataset or vice versa. Uh, the most important concept defined by Lightsaber, the base dataset class, is this idea of transforms and filters. Together, transforms and filters supports a set of composable functions that can be used to transform the data at runtime. The main difference is that filters can work on both the feature data and the target subsets and are typically executed during the loading of the dataset from raw feature file into the base class. Transforms only act at runtime in a transient manner while accessing a single element. These two differences provides a lot of power and functionality to the end user. However, in most cases, filters are more than sufficient for most users. Filters accepts as arguments data and target, and then it provides other keyword functions which can be set as before and always returns data and target. This allows users to define a chain of such filters in a composable manner, some of which are already defined in Lightsaber. Some of the most important filters have to deal with filling NA, also chaining together any scikit-learn preprocessor through the filter preprocessor argument. It also supports allowing the user to get only the last time point, which are especially useful for training embedding models such as Met2X. In a corollary, we also provide a high-level utility that is more useful to work with scikit-learn models. Base dataset with the appropriate filters can be used to access such datasets, but this class SK data loaders makes it much more easier for a user who's more concerned with training sklearn models to work with a simplified interface. Here you see an example where we create a training data loader where we only add certain amounts of scikit-learn preprocessor. In this case, we just use a standard scalar. But in typically, we can use any amount of such scalars. And here you see we use sum to flatten our time temporal data. Moving on to model training, Lightsaber provides task-specific model wrappers. We support both scikit-learn and PyTorch models. We accept any kind of base scikit-learn or PyTorch models, allowing the user to focus only on their logic of the model, and we wrap this through this model trainer to provide capabilities such as calibration, tuning, and other post-hoc analysis hooks. And finally, these are then run through provided functional training routines that are tailored to specific tasks. Again, such routines conduct the training with complete audit trail and model tracking and logging the appropriate metrics. Also, one key important thing is that we try to separate the experiment logic from the model definitions that are provided through the wrapped models as we just discussed before, and engineering features. So for example, in PyTorch, we can use any PyTorch lightning trainers. Now that we have seen how powerful Lightsaber is, we can move on to see a complete example about how to train a model for in-hospital mortality for Mimic 3 data using Lightsaber.
We are going to see how to use the Lightsaber framework to train and register a model. We will delve into how to interact with these deployed microservices in the latter part of the segment. Note that this training framework is integrated with another portion of the system called Service Builder. Service Builder is a separate component that deploys as microservices those trained models that attack for production. In the very beginning, as you can see, our cluster has no models registered. Since training the model takes a few minutes to complete, I am going to kick off this notebook. In the meantime, I will go over the different components of the notebook. The task that we are trying to train the model for is in-hospital mortality prediction using the MIMIC3 dataset. In the very beginning, we specify the data directory as well as the configuration files. The data directory contains train and test files. The YAML configuration specifies the data that has already been extracted from cohorts. Next, we see the data transformation utilities. Users can either use pre-packaged filter and transforms or write their own and pass it at runtime as we have over here. At this point, we have defined the filters and transforms to be used. We have also read the train and test dataset. We now need to define our model. In our case, this is an LSTM model with a dropout of 0.1. We also specify several other hyperparameters that are needed for our experiment. We are now ready to train the model. Here we specify the experiment name, the registered model name, and the run name. After running the cell, we should have a registered model in our MLflow UI. Since the training still has a few minutes remaining, we can briefly see the artifacts associated with our experiment that has just been created through this notebook. This is the experiment that we have just created. On viewing the experiment, we can see that there are several metrics as well as a page for artifacts. Now that we see that the training is complete, we also see that the model has been successfully registered in the MLflow UI. We can now go and check our MLflow UI to find the registered model. If we go to the experiments page, we can see a link that allows us to directly go to the model that we just registered. Next, let's try to deploy this model as a microservice. I am now going to set the production flag to true. As I mentioned earlier, there is another component called Service Builder that automatically deploys the service as a microservice once this flag is set to production. Now, let's go to the Kubernetes dashboard. If we go to the cron jobs, we see the cron job has created a job. And further, if we go to the Services tab, we see that a service has been created for this model. Now, if we go back to the MLflow UI, we see that there is a model endpoint that has been created. We can use this model endpoint to interact with our microservice. We now see the Swagger page, which shows us a few different APIs that are available. Since we want a prediction, we can go to the Predict API pass along the patient ID that we want a prediction for, and execute this API. What we get in response is predicted values, a prediction for 0 as well as a prediction for 1. In summary, we saw how to use Lightsaber to train a model, which we did through the notebook that we saw. We then deployed the model as a microservice, which we did through the UI by setting the flag to production. And finally, we interacted with the model to get a prediction for our input patient ID, which we did through the Swagger UI. Thank you.
Thank you, Rachita. I'm Nelson Bore, and I'm going to take you through Service Builder details. Service Builder component is responsible for converting registered models into microservices. It achieves this through a number of automated steps. The diagram shown in the chart helps us to follow these steps and see what occurs in each step. I will walk through each step starting from step number 1. In step number 1, Service Builder comes with an inbuilt post-registration hook in the form of a cron job, which is configured to listen for a deployment-ready model in the model registry. Identification of deployment-ready model is done using a production tag being set on the model by the machine learning researcher. A registered model has metadata that includes the model binary file, its dependencies, and related artifacts, among others. In step number 2, upon finding a deployment-ready model in the registry, the post-registration hook extracts model and its dependencies from the model registry and packages the model as a microservice in a Docker container using a framework called Model Wrapper. In step number 3, upon successful packaging of the model as a container, the execution flow proceeds to model deployment in a target cloud cluster, e.g. Kubernetes or OpenShift. The deployment process makes use of a base deployment image, model wrapper, as well as actual container created in the previous step. Upon successful deployment, a callback function updates model metadata in the model registry with deployment status and model access point. In step number 4, using the model endpoint, potential users, for example data scientists or product managers, can interact with the model now deployed as a microservice through a Swagger-based interface. In the interface, they provide inputs to the model, for example patient ID, which is then passed to the model for prediction, and response is returned to the user. In summary, we have seen how the Service Builder automatically converts deployment-ready models from model registry into interactive microservices deployed in a cloud environment. Now back to Partha.
In this video, we saw a demonstration of DPM360. A detailed description of the example use cases, architecture, and roadmap is available in the public GitHub repository shown in the screen. It also contains our initial implementation of DPM360. In the coming months, we plan to execute on our published roadmap for DPM360 and report on its effectiveness at improving collaborative research and rapid commercialization of disease progression models. Thank you.